Frequency modulation is a technique in communication in which the amplitude of the carrier wave or the radio frequency wave is kept constant and the frequency of carrier wave is varied in accordance with the instantaneous value of the message signal or the modulating signal. When this kind of modulated wave is aired, it is received by the radio receiver. Now, in the radio receiver, one has to retrieve the original modulating signal or the message signal from the incoming FM signal. So, the function of FM D Modulator is basically change the frequency deviations that are present in the FM wave into the corresponding voltage variations. And the basic requirement in this process is that this conversion should be linear. It means that the voltage which is produced by the FM demodulator should be exactly in proportion with the frequency of the input FM signal. That is, if the frequency of the FM wave is increasing, the output of the demodulator should increase, and if the frequency of FM wave is decreasing, then the output voltage of the demodulator should decrease in perfect proportion. The basic circuits for FM demodulation are slope detector and balanced slope detector. So in this presentation, we are considering the operation of slope detector and balanced slope detector. In figure 1, the basic circuit of a slope detector is shown. Slope detector is a simple tuned circuit. Tuned circuit is a circuit containing a combination of an inductor coil and a capacitor. So there are two tuned circuits in this circuit of slope detector. This is the primary coil and this is the secondary coil. Across the primary coil, capacitor C1 is connected. So this is one tuned circuit. And across the secondary, another capacitor is placed. So this is the second tuned circuit. The primary tuned circuit is tuned at frequency Fc, which is the carrier frequency of the FM wave. Or we can say that if Fc is the central frequency of the FM wave, then the primary circuit is tuned at that frequency. And the secondary circuit is tuned at a frequency Fc plus delta F. The secondary is tuned at a slightly different frequency and we have named it as Fc plus delta F. In figure number 2, the selectivity curve of the secondary tuned circuit is shown. This is the selectivity curve of the secondary tuned circuit. And from this figure, we can see that the resonant frequency is kept at Fc plus delta F. This is the resonant frequency of the secondary coil. As we can see from this figure, this is the frequency of the carrier signal, or we can say this is the central frequency of FM. This point is the highest frequency of the FM signal, and this point gives the lowest frequency of the FM signal. So in this span, the frequency variation of the FM signal lies. As we can see from this figure, the resonant frequency of the secondary coil is kept higher than the highest frequency of the FM wave, and it is done in order to keep the entire frequency variation of the FM wave on the linear portion of the selectivity curve, because we know that during or around the peak of the selectivity curve, there is a drastic change in the curvature of the curve. So if we keep the resonant frequency around the highest frequency of the FM wave, then the curve will not be linear in this portion. Hence, the output voltage will not be directly proportional to the incoming frequency, because that is our prime requirement, that the output voltage should be in direct proportion with the incoming frequency. Therefore, in order to comply with this requirement, the frequency variation should be kept along the linear portion of the curve. Therefore, the resonant frequency is kept much higher than the highest frequency of the FM wave. Now, we know that when the incoming frequency is increasing, we can see from the figure, if the incoming frequency is increasing, suppose the incoming frequency is highest, then according to this curve, we can see that when the frequency of the incoming wave is highest, then the corresponding output voltage is also at the maximum point. Or we can say that the amplitude of the FM signal or the output signal will be highest. At carrier frequency, corresponding to the carrier frequency, the voltage is this much. Therefore, correspondingly, the amplitude of the signal will be at this point. And at the point where the frequency is minimum, the amplitude of the output signal will be like this. Therefore, we can say that the amplitude of the RF variations, these are the RF variations, amplitude of the RF variation according to the modulated signal, or the amplitude change of the RF signal is according to the change in the frequency of FM signal. So we can say that the envelope of this wave is the message signal or the modulating signal. As we have studied earlier in amplitude modulation, the output signal, this is the output signal, and it is somewhat like amplitude modulated wave. When we study the amplitude modulated wave, then we see that the form or the shape of the amplitude modulated wave is like this. Therefore, what we are getting at the output of the circuit or the slope detector is the amplitude modulated wave. And we know that in order to retrieve the original signal from the amplitude modulated wave, we normally use a kind of circuit which contains a diode and an RC circuit. This is a combination of RC circuit and this is the diode. So at the output or at this point we are getting this amplitude modulated wave, and in order to convert this AM wave into a normal modulating signal, we have to use the diode and RC circuit. The use of the RC circuit is that in this case, if we study this wave, we know that at this point the amplitude is maximum, but after that it falls to zero. Again it rises and again it falls to zero. So we have to smoothen out these variations. We want only this envelope of the signal, because this is the actual modulated signal. So in order to smoothen out these RF variations, what we have to do is to remove this portion where the amplitude goes to maximum and then comes to zero. So in the RC circuit, the capacitor, actually when some output voltage is applied at this point, the capacitor charges up to the peak voltage. And during the portion when the voltage falls to zero, the capacitor discharges across the resistance. In the portion where the amplitude falls to zero, during this portion the capacitor starts discharging across the resistor R1. Therefore, these variations or these fluctuations, RF fluctuations, are smoothened out in the output of the circuit. So we will be getting only the envelope of the signal, or this is the actual message signal. Now the only requirement is that the time constant of this circuit C3R1, it must be slow enough to keep the RF ripples as small as possible. That is, it should be very slow. It should discharge very slowly in order to smoothen out these fast variations in the during this time when the RF signal goes from top to bottom and again comes to top, the RC circuit should slowly discharge. Therefore, these fluctuations will smoothen out. But it should be fast enough to follow the fastest variations. So it should be a combination of these two requirements, and that gives us the exact value of time constant of the RC circuit. Slope detector is the basic circuit for Fm D modulation. It is a simple circuit and it gives us a good understanding of basic concept of Fm D modulation. But there are some shortcomings and disadvantages associated with this basic circuit. The main disadvantage is that it suffers from the lack of linearity. As we have mentioned earlier, the main requirement is that there should be a direct connection between the frequency deviation and the output voltage. That is, the output voltage should be in direct proportion with the frequency of the incoming signal, and that condition is satisfied only when the frequency deviation of the FM signal falls on the linear portion of the selectivity curve. But we can see that in the selectivity curve, only a limited portion of the curve is linear. Rest of the portions have a curvature. Therefore, we can use or utilize a limited portion of the selectivity curve. The second shortcoming is that this circuit responds to all the stray amplitude changes in the incoming signal. If due to some noise or stray sound or stray fluctuations, there are some fluctuations in the amplitude of the FM signal, actually that should be perfectly constant. The amplitude of FM wave should be perfectly constant. But if there are some random
fluctuations in the amplitude due to stray sound or stray signals, then the slope detector circuit does not distinguish it, and the circuit responds to these variations or these noises. Therefore, these stray changes in the amplitude, they are reflected in the output, causing a severe problem of noise at the output of the circuit. The other disadvantage is that it is very difficult to maintain two different tuned frequencies or two different resonant frequencies in a single transformer. As we have seen that we are using a transformer and the primary coil is tuned at frequency Fc and the secondary winding is tuned at frequency Fc plus delta F. So it is quite a difficult task to maintain two different resonant frequencies of a single transformer. So these are the disadvantages. But as this is the primitive type of circuit, so it is a simple circuit, and these disadvantages or the shortcomings are improved in the next step of this process, that is and the next step is the balanced Fm demodulator. Balanced slope detector is a combination of two slope detectors. These two slope detectors are connected to the opposite ends of the secondary of the transformer. As we can see in the figure, this is the primary coil, and this primary coil has a tuned circuit. It is forming a tuned circuit which is tuned at the central frequency, that is Fc. This is the secondary coil, and to the two extreme ends of the secondary coil, two circuits of slope detector are connected. That is, this is one circuit of the slope detector, and to the other end of the secondary, the other circuit of slope detector is connected. So these two are the two circuits of slope detector connected back to back. This circuit is named as T dash, and the lower circuit is named as T double dash. Now the important point is that the circuit T dash is tuned at frequency Fc plus delta F. This is the resonant frequency, and the lower circuit or the circuit T double dash is tuned at frequency Fc minus delta F, where Fc is the resonant frequency and Fc plus delta F, as in the case of slope detector, in this case also Fc plus delta F is quite higher than the largest frequency in the FM wave or the incoming frequency modulated signal. And in this case, Fc minus delta F, which is the resonant frequency of the lower circuit, it is much smaller than the lowest frequency deviation or the lowest frequency present in the incoming FM wave. As we can easily understand on lines with the uh, principle of slope detector, why this kind of adjustment is made. This adjustment is made in order to keep the frequency variation of the incoming FM signal strictly contained inside the linear portion of the selectivity curve. It is made in order to keep the frequency deviations of the FM wave uh, inside the linear portion of the selectivity curve. Now D1 and D2 are the two diodes. R1 is the load resistor of the upper circuit and R2 is the load resistor of the lower circuit, that is of diode D2. The output voltage is V0, which is the difference of voltage across R1. VR1 is the voltage produced across resistor R1 and VR2 is the voltage produced across the resistor R2, and the output voltage is naturally VR1 minus VR2. In figure A, the selectivity curve of transformer T dash is shown. As I have mentioned earlier, the tuned circuit T dash is tuned at frequency Fc plus delta F. This is the resonant frequency of T dash. So at this frequency there is peak of the selectivity curve, and this figure shows the selectivity curve of tuned circuit T double dash, which is tuned at Fc minus delta F. So at frequency Fc minus delta F, the peak of the selectivity curve falls. Now let us see what happens in the circuit when the incoming frequency is equal to the central frequency or the carrier frequency. Suppose the incoming frequency is Fc. When it is Fc, then suppose in the tuned circuit T dash, the voltage is V0. From this figure, we can see that when the frequency is Fc, the output voltage of T dash is equal to V0. In this figure B, for the selectivity curve of T double dash, when the frequency is Fc of the incoming signal, then the output voltage of this circuit is V0 dash. Now we can easily understand that in this figure, Fc lies as much far away from the resonant frequency as Fc lies from the resonant frequency Fc minus delta F. That is, the distance between Fc or the separation between Fc and resonant frequency in this figure is equal to the gap between Fc minus delta F and Fc in this figure. Meaning to say that when incoming frequency is Fc, the output voltage of upper circuit V0 and the output voltage of the lower circuit, the output voltage V0 dash, these both values are equal. V0 is equal to V0 dash. Hence, diode D1 will be getting voltage V0 from the circuit, from the output of tuned circuit T dash, and diode D2 will be getting voltage V0 dash from the output of tuned circuit T double dash. But the values of these two voltages are equal. Hence, we can say that if we see the circuit of balanced slope detector, as both the voltages across D1 and D2 are equal, the currents will also be the same. But the directions of these two currents through D1 and D2 are opposite. Therefore, we can say that the voltage VR1 and voltage VR2 are equal as the currents are equal. Hence the output voltage, which is equal to VR1 minus VR2, will be 0. Hence we can say that when frequency of incoming signal is equal to the carrier frequency, the output voltage is 0. Now let us see what happens when the input frequency is higher than the central frequency, or it is higher than the carrier frequency Fc. Let us say that the frequency of the incoming signal is highest. This is the frequency of the incoming signal. At this point, the voltage across T dash is equal to V1, and at this point, the voltage across T double dash is V1 dash. As can be seen from these two figures, V1 is naturally greater than V1 dash. Therefore, the current through the diode D1 is greater than the current through the diode D2. Therefore, VR1 is greater than VR2. Hence, for the condition Vi greater than Fc, that is the incoming frequency greater than the carrier frequency, the output voltage will be positive. Similarly, we can say that when the frequency is at its lowest, this is the lowest frequency, or the frequency is decreasing, and after decreasing it comes to the minimum value, the voltage across the tuned circuit T dash is V2. This is the value of V2 on the upper circuit, and at this point, that is the minimum frequency, the output across the transformer or the tuned circuit T double dash is V2 dash. As we can see from this, comparing these two voltages, V2 is smaller than V2 dash. That is, the voltage across diode D1 is less than the voltage across diode D2. Hence, the current in the upper circuit is smaller and current in the lower circuit is greater. Hence, the value of VR1 is smaller than VR2. Hence, the output voltage, that is V0, which is VR1 minus VR2, will be negative. Hence, we can say that when incoming frequency is Fc, the voltage is 0. When Fi is greater than Fc, the voltage is positive, output voltage is positive. When Fi is smaller than Fc, the output voltage is negative. We have considered the extreme cases. This is the maximum frequency and this is the minimum frequency. If we are considering the intermediate frequency, then the output voltage will be lying in the intermediate range. But the main thing is that when Fi is greater than Fc, then the output voltage will be naturally positive, and when Fi is smaller than Fc, then the output voltage will be negative. That is the main point of concern in the functioning of this balanced slope detector. As explained in the previous slide, when the frequency of the incoming signal is equal to the carrier frequency, then the output voltage is 0. When it is greater than the central frequency or the carrier frequency, then the output voltage is in the positive direction or the positive value. And when the incoming frequency is less than the carrier frequency, then it is in the negative direction. And when the frequency exceeds the resonant frequency by some means, the frequency exceeds Fc plus delta F, or it exceeds Fc minus delta F, which are the resonant frequencies of the two tuned circuits, then naturally the output voltage will be decreasing on this side and similarly on the other side. This kind of frequency response of the balanced lobe detector is known as S-shaped frequency response, and this is the prime requirement for the output response of a balanced slope detector. And this kind of frequency response will be required in all the Fm demodulator circuits, which we will study in later stages. The main disadvantages or the shortcomings of balanced slope detector is that we have to maintain three resonant frequencies in primary and secondary, one for the primary circuit and the other two for T dash and T double dash. The second shortcoming is that the linearity is better than that of the slope detector, but it is still not good enough. And the third is that, as in the case of slope detector, in this case also amplitude limiting is not provided. That is, if there is some kind of amplitude variations in the FM wave due to stray sound or stray signal, this circuit is not capable of distinguishing it and responds to these amplitude variations, and this kind of fluctuations in the amplitude result in fluctuations or some noise in the output of balanced slope detector. Okay.